Okay, so next week we're going to start looking at, well, probably today, we're going to start looking at Roald Hoffman's presentation of band structure. And so please go get a hold of this article, How Chemistry and Physics Meet in Solid State, and start reading it. This is really worth your time. Please make an effort to dig into this article. A lot of the figures and examples that we're going to do are taken directly from this text. Okay, so this is pretty good stuff. Just a quick review of what we talked about last time. We analyzed the Coulomb potential in a crystal lattice. And in a crystal lattice, you have many different interactions for the cations and the anions with the neighboring cations and anions. And some of those neighboring cations are positively charged, some are negatively charged, depending upon the number of nearest neighbors away. And if you add up all of those interactions, you get something called Madelung potential. This is the Coulomb potential for that arrangement of ions in the gas phase, so in a vacuum. And that's why the dielectric constant here in this expression is the gas phase dielectric constant. We also consider polarization effects in the subsequent presentation. And that constant here, the number of nearest neighbors and their distance away, is a simple geometric factor, and it is dependent upon the crystal structure. So if you have different crystal structures like rock salt, wurtzite, and sphalerite, you get different geometric constants, okay? And you can see that something with a higher geometric constant is going to have a larger Coulomb potential. Okay, so these various structures here, rock salt, wurtzite, and sphalerite, that constant is decreasing. And that makes the rock salt structure a structure that you see for ionic materials, because you get better Coulomb interactions in that geometry. Okay, so you can estimate the importance of the ionic bonding or the attraction just by looking at that Madelung constant. We looked at how that plays out in a sort of thermochemical cycle using the example of sodium chloride. Remember, it's actually uphill to generate two ions in the gas phase, even when those ions are sodium plus and chloride minus. That electron transfer is uphill by 1.7 eV. That's a lot of energy. And really, the energy for making sodium chloride comes from the Madelung potential. It's all about the electrostatic binding of that lattice, 16 EVs. Now that is modulated by the polarization of the crystal. So the atoms rearrange their electrons while maintaining the symmetry in the case of sodium chloride. And that polarization of those electrons does a lot to change the stability of those charges and the bonding of that lattice. And then there's also these covalent effects, right? There's the development of the bandwidth. Bandwidth is a molecular orbital sort of covalency issue. It's all about orbital overlap. And in the case of this empty orbital band up here, let me see if I have a laser pointer. There we go. These empty orbitals that make up the conduction band of sodium chloride, they come from the sodium plus ion. So these are 4s, 3s orbitals from the sodium ion, and they have a wide bandwidth because s orbitals make good bonds. P orbitals, not as good at covalent bonding. D orbitals, even less. F orbitals, even less. And that changes the bandwidth. Strong orbital overlap gives large energetic splitting between antibonding and bonding. And we'll look at this a little bit more detail in a little while here, but that leads to this, the width of the band. Okay, and you do all the math on all of those various contributions and you recover the band gap, which is the distance between the top of the valence band and the bottom of the conduction band. All right, so Madelung potentials are really a big deal. They sort of set the stage for what the band gap is in the material, and then these polarization and bandwidth effects come in after the fact.
I have a quick question about that slide.
Yeah.
So is there a reason that there's a 2x in parentheses after the Madelung potential?
You have to consider the binding of both ions, I guess. So if you were to calculate, this potential is really for one, right? It's for this guy right here. And I guess you have to calculate it for both to recover the lattice potential.
Okay, thanks.
Yeah. Okay. If you do the thermochemistry on this, right, here's the same sort of expression. We're going from the neutral atom to the charged atom. You can use the ionization energy and the electron affinity to do that transformation. And then there's the lattice energy, which is the energy of taking those gas phase ions and making a solid crystal. And the sum of those recovers the heat of formation of sodium chloride. Lattice energies are shown over here on the right, and the trend that we discussed is that the biggest contributor to these changes are the bond distance, right? The separation between the ions dictates how strong the Coulombic forces are. It goes as 1 over the separation. And then secondarily, electron affinity and ionization energy. If you have a 2+, 2-, or a 3+, or a 3- ion, you can multiply those potentials by 2 or 3. And that gives much, much larger lattice enthalpies for things like scandium nitride, where you've got a 3+ and a 3-. So magnesium oxide, calcium oxide, strontium oxide, very insoluble thermodynamic sinks. Magnesium oxide burns, you can burn magnesium metal in a carbon dioxide atmosphere. Amazing. There's this stuff called thermite, which is used to weld steel underwater. Amazing. Welding underwater with a solid. It makes magnesium oxide. Huge driving force to make magnesium oxide because of that lattice energy. 2+ and 2-. Small cations, small anions, massive energies. Okay, very useful principle. All right, so I wanted to keep talking about photoelectron spectroscopy. We showed an example of an X-ray tube. Maybe I'll just jump back to that. We showed this example of an X-ray tube where electrons collide with a metal. The collision knocks electrons out of the atoms in that metal. And if you generate a hole, a missing electron in one of those core orbitals, you can get a recombination event where a valence band electron drops down and X-rays come out. And depending upon the depth of the hole, whether it's say in a 1s or a 2s or a 2p level, that recombination event gives a very well-defined X-ray emission energy. So magnesium, aluminum, zirconium, silver, etc., they have K alpha or L alpha radiation of these various energies. It's a well-defined energy, and that's a standard way of generating X-rays in a lab. If you want to make a laboratory source, the single crystal diffractometer has a copper K alpha radiation source and an aluminum source, I think. I don't remember what the other source is, but those are standard X-ray tubes. Now, you can also generate X-rays using a synchrotron, and a synchrotron provides a much, much brighter source of electrons and gives you a lot more flexibility about the energy range that you use. So this is actually a series of diagrams stolen from the European Synchrotron Radiation Facility's website. The synchrotron is in Grenoble, France. It's composed of 2 rings here. This accelerating ring, oops, this laser pointer is a little bit wonky, and then this insertion ring here. And basically what happens is that this thing, which is about 2 miles wide, okay, this is a hallway. I think there are people, here's a person drawn to scale in one of the sections of this thing, this little black figure. So this thing is massive. It's about 2 miles wide, and there's a beam of electrons being accelerated around this ring. Okay, there are a bunch of parallel plates that generate electric force pushing the electrons around this ring. And as they go around the ring, they pass through focusing magnets that sort of probably like quadrupolar magnet systems or hexapolar magnet systems that are oscillating back and forth, just like in a mass spectrometer, that focus down the moving charges. And then they go by other magnets that bend them. Okay, they continue getting focused and bent, and then sometimes they go past this thing called an undulator. Now, when the electron is pushed off axis, when it goes past the bending magnet, it releases a tremendous amount of energy as X-rays. Okay, so the magnet is diagrammed here. The electron packet that flies by produces synchrotron light. So the act of bending it, or the act of running it past this undulator. An undulator is a bunch of magnets with oscillating orientation. So it goes past this collection of magnets, and the motion as it goes past those magnetic fields that are going back and forth causes it to produce X-rays. This sort of a device produces a much more controllable energy range. So depending upon how closely spaced the magnets are, you can actually change the frequency of light that's being emitted. Here you get a much wider range of energies coming off. You can also get angle control with these types of devices, okay? And so you can see here in this diagram, these black tubes. These tubes collect the X-rays that are being produced at the bending magnets, and then they run out of the synchrotron into these hallways. And the hallways, or they call them hutches, is where people do experiments. Okay, so the X-rays come off of the beam, and then they're collected and filtered and focused for whatever purpose. You know, some experiments you want high energy, some experiments you want low energy. And so the hallway is paired to the X-ray generating element of the synchrotron. And then the scientists take advantage of those. So there's many of these stations around this 2 mile wide beam, and people come in and sit down, and the synchrotron is sending packets of electrons around, generating X-rays all day and all night. You can imagine that operating something like this is not a small endeavor. They're hugely expensive. Getting a week of time on some of these things is worth hundreds of thousands of dollars of research funding. So so typically in a laboratory source, you know, you have an X-ray that comes in with a very specific energy that promotes a core hole, generating this photoelectron. We're going to talk a little bit about ultraviolet photoelectron spectroscopy. But with a synchrotron, you have much finer control over the types of X-rays that come in, the width of energy over which the X-rays come in, and things like orientation and whatnot that make much finer spectroscopies possible. Okay, so let's just review this picture for a second. Each one of the peaks that you see here in this diagram corresponds to a different core level. Okay, so X-ray comes in, collides with the electron, and sends it off into space. It shoots out of the material. You measure the kinetic energy of that electron, and then from that, you can determine the binding energy. Each one of these core levels is very deep compared to the Fermi energy in the material. 500 electron volts, 300 electron volts, huge amounts of energy to rip an electron out of those levels. And each level is spaced, you know, here's titanium 2s, titanium 2p. There are big differences between those levels in those atoms, and that makes them sort of useful for identifying the elements. So the other part of this is this background that we mentioned. The background here comes from scattering. Okay, so here's a diagram illustrating that. So X-rays penetrate through the sample. You know, you can put your hand in front of an X-ray beam and the X-rays will pass through it. So the X-rays penetrate very deeply into the sample. And as they go along, they collide with the various atoms there with relatively low probability. And then they generate electrons. Those electrons can come streaming out of the crystal, but sometimes they'll collide with another atom before they escape. And that's because charged things like protons or electrons, they have a much higher scattering probability than photons do. So the photons penetrate deeply into the solid. The electrons are generated by this collision and the emission process, and then they either escape cleanly or they collide once, twice, 3 times before they get out, or they don't escape at all. Okay, and so the deeper you go into the solid before the collision process happens, the less likely the electron is to escape. And people say rule of thumb is that for most substances and most photoelectrons, you get about in that first 10 nanometers beneath the surface, electrons can escape from the crystal. Deeper than that, nothing happens. All the electrons are captured. And so as a result, this photoelectron spectrum is really the signature of the atoms found right at the surface of that material. Now, some of these electrons do escape following collision events, actually a lot of them, okay? And that's where this background signal comes from. So if you're colliding with the titanium-2p orbital, those electrons start flying out with 450 electron volts of, or come out with a kinetic energy that corresponds to 450 electron volts. But then some of the time, those electrons collide and they deposit some of that excess energy into the crystal. And then the electron continues. And when it comes out, it has a lower binding energy, it has a lower kinetic energy because it left some behind in the crystal than it would have if it came out cleanly. And so a lower kinetic energy corresponds to a higher binding energy. And as a result, you get signal here on the left-hand side, the higher binding energy side of this titanium-2p resonance. Same is true up here for titanium-2s and oxygen-1s. These photoelectrons also are colliding, giving up some kinetic energy to the crystal, and they come out with apparently higher binding energies. Okay, so this sort of like increasing background after each of these levels is passed is a consequence of scattering before the electron comes out of the crystal. So it turns out that the scattering probability, or the mean free path of the electron, is energy dependent. And so if you have an electron with a kinetic energy of 50 electron volts, the mean free path for that electron is really small. If your electron has even less energy, its mean free path goes up, or higher energy, its mean free path goes up. Now, I don't really understand why this is the case, but it happens to be true that the mean free path, or the probability of a scattering event, is dependent on the kinetic energy of the electrons coming out. So people have learned to take advantage of this because you can change the X-ray energy that you use to generate the photoelectron. And for a given orbital or state that you're trying to probe, changing the X-ray energy, the source of excitation, will change the kinetic energy of the electrons that come out of a given orbital. Okay, so you can modulate the leftover kinetic energy by changing the energy of the excitation source that's used to generate a photoelectron. So if you tune that energy around, you change the electron energy of the emitted photoelectron, and that changes its mean free path. Okay, so that allows you to do surface sensitive work. All right. So the result is, if you're doing careful surface science and you want to look right at the surface level, you get your electrons down here and you can look at the atoms that reside in the first couple of angstroms, enhance their intensity in the signal, and ignore the bulk. So here's an example of that, looking at a silicon wafer. So here's a diagram of that sample. There's a silicon substrate. You've got a nanometer of silicon dioxide. You've got 2 nanometers of hafnium dioxide and 2.5 nanometers of silicon nitride. Okay, this is a coating that goes on chips probably used to make transistors of some kind. These sorts of materials, hafnium dioxide, are very high dielectric constant materials with a very strong, robust chemistry that prevents the penetration of other ions. Okay, so it's sort of like a very strong coating that allows large potentials to be dropped across it for transistor purposes. All right, so this type of a sample, if you take it to the to a photoelectron spectrometer, you put it in there and you look at it with aluminum K alpha radiation versus aluminum L alpha radiation, you're changing the photon energy from 1487 eV in this case to 2984 EV in this case. And if you have a much higher energy source in this aluminum L alpha radiation example, then the kinetic energy of the electrons is going to be much higher. And notice the spectrum here, there's actually signals for silicon nitride, oxide, and then the bulk silicon. Same signals over here, but the ratio of those peaks has changed quite a bit. Now there's very little elemental silicon. Here there's a lot more. And we know that this sample looks approximately like this. And so the increased elemental signal shown in blue here is a consequence of the fact that the photoelectrons have a lot more kinetic energy when they escape. Okay, so they scatter less. Whereas in this case, the kinetic energy is lower and they scatter more. And you don't see the stuff that's beneath the surface. You only see that surface layer. Okay, so you can play games like this to try and study your sample and decide, what is it that I'm looking at? What is the arrangement of the layers in the sample? And even if we didn't have this diagram, if I saw this, this pair of figures, I could tell you that it's silicon dioxide on top of silicon nitride on top of silicon, or I guess the other way around. All right, so that's a pretty standard trick that people use to do surface analysis. All right, so we're going to spend some time talking about ultraviolet photoelectron spectroscopy. This is somewhat less frequently used, but it's a way to probe the valence band, or the states near the HOMO of a molecule or the valence band edge of a semiconductor. So here's our diagram again. Now we're looking at a solid where we've got the Fermi energy shown, the vacuum level. Here's the valence band, and this time I've sort of ignored the core levels. I haven't drawn them in explicitly because we're not going to do core level spectroscopy. We're going to look at the valence band, but there are core orbitals down here. So the same sort of thing happens. An ultraviolet photon or a low energy X-ray comes in, collides with an electron in the valence band, promotes it, and you get this emitted electron that's got kinetic energy. There's a work function, and there's a binding energy. Binding energy is defined by the difference between that hole and the Fermi energy. The work function is the difference between the Fermi energy and the vacuum level. So in a molecular ultraviolet photoelectron spectroscopy experiment, you have the same exact thing, except now we have well-defined molecular orbitals as opposed to a band of orbitals. And so in the case of benzene shown here, I've shown you the MOs. You know that there are 6 MOs made up of those 6 p orbitals in a ring, and they have this symmetry where it's singly, doubly, doubly, and singly degenerate, adding nodes as you go up. Because there are 6 electrons, each one of these MOs has 2 electrons in it, and these ones here are empty. And so I've shown them here in this diagram. Again, this is the totally symmetric molecular orbital down here, size 0. This pair of levels is the E prime set, I think, psi 1, and so forth. So in comes your photon again, this time promoting an electron, and I've shown here an electron coming out of size 0. You could also do it for psi 1 if you wanted. And that photoelectron goes flying out with some kinetic energy. And then you measure the separation between the vacuum energy and the various orbital levels to measure their depth. Those are the molecular orbital binding energies. All right. These energies are in the range of like 1 to 10 EVs, okay? XPS, 100 to, thousands of EVs. All right, so much, much lower energy. All right, so if you take a UPS spectrum or ultraviolet photoelectron spectrum of benzene, you'll see something like this or something like this, depending upon whether the benzene is a vapor or whether it's a solid. So you can take a tube full of vapor, shine strong, high energy UV light source on it, and out will come photoelectrons that have these various energies. Shown here is the binding energy. And you'll get these sort of like peaks with teeth on them. And actually these teeth correspond to vibrational energy differences. So CC double bond in benzene, vibrational frequencies around 1600 wave numbers. And you've got CC and CH bonds, and those energies, if your source of ultraviolet photons is monochromatic enough, you can see that type of structure here. When you go to a solid, you get a different situation. Okay, you don't see the vibrational structure anymore, and also there's a slight shift. So you don't see this well-resolved dip, but there's the analogous dip here. Now it's at slightly lower energy than it is here. Okay, and so some of the same sorts of features are at play here. Before I show those, maybe I'll just point out that you see 3 peaks for the various different energy levels that you're ionizing. This one and this one correspond to the lowest this guy is going to correspond to this level here. Oh boy, I need to turn off this laser pointer. Yeah, this level here, you guys can see my mouse, right? Yeah. So this level here is the lowest energy binding, right? The electron binding to this level is the smallest, since it's all the way on the left of the diagram, and that corresponds to the HOMO of benzene. And then as you go deeper, you go down in energy. Here's another one of the aromatic levels, a couple of EVs lower, and then so on. There are other levels, not just the ones associated with the pi system, that you can also probe this way. When you make a solid, the energy of binding changes, okay? And there are 2 different ways that happens, one of which is because of scattering. That can lead to a background signal that can cause some poor resolution. And then the other is polarizability. Okay, so when you promote an electron out of a solid sample of benzene, the hole that you leave behind is sort of solvated by the dielectric medium. And that changes the energy of generating that hole, and that causes a slight shift in that spectrum. So the polarizability of the solid can influence the binding energy. So that's basically caused by the dielectric change in the medium. Gas phase or the vacuum is has a low dielectric constant compared to benzene does. Let's see here. Okay, so if you really want to do fancy pants photoelectron spectroscopy and try and do molecular orbital structure solution and that kind of thing, these measurements are typically done in the gas phase. Here's an example of the ultraviolet photoelectron spectrum of a metal. So this is gold, and this turns out a gold crystal that has the 111 surface pointing up. So the photoelectrons are escaping along that direction. And again, the X-ray comes in, promotes an electron, it has kinetic energy, etc. And you end up with a UPS spectrum that looks something like this. Okay, so it starts off at 0, it goes up, you get this pair of bumps here, and then it continues to rise and then until it suddenly falls down. So this is not just some weird truncation or bad drawing. Actually, the energy goes up and then all of a sudden you don't get any more photoelectrons. And, you know, these sorts of measurements can be referenced to some other species present in the sample. But typically what's done is you know the photoelectron energy, sorry, you know the photon energy of the ultraviolet photoelectron spectrometer. And then you look at the position where these photoelectrons are no longer coming out and the onset where you just begin to see electrons that essentially have 0 binding. Okay, so at the top of this band of filled levels, you reach the Fermi energy. That is a binding energy of 0. Right? Binding energy is defined by the difference between the level you're probing and the Fermi energy. So right at the Fermi energy, any electrons that you're promoting have 0 binding. So when you get this curve shape here, the onset of photoelectron generation is the Fermi energy, and it's set to 0 as in the binding energy scale. Okay, so these are the most weakly bound electrons. As you go deeper into the valence band, you're going this way on the binding energy curve. You get this sort of signal here, and then you end up seeing a lot of background electrons. These are scattered electrons in the same way that they were from that X-ray photoelectron spectrum experiment. And pretty soon, the binding of those electrons is so great that they don't come out anymore. So you know you have a 21.2 eV photon, and this energy of 16 electron volts, where the spectrum dies, the difference between those two things corresponds to the work function of the material. Right? So if we take the work function and the binding energy, and you go down, the sum of those two things goes below 21.2 electron volts, the photons do not have enough energy to kick electrons out of the solid anymore. Any deeper than that, you don't get any more photoelectrons, and the spectrum like suddenly truncates. So under that assumption, you set this to 0, you measure this width here of 16 electron volts, and you determine the work function of this sample being 5.2 eV. Now, this signal here, which sits on top of the background of scattered electrons, which is a function that can be fit, this is the valence band, or whatever orbitals you're probing. And so this two-peaked character here reminds me a lot of the combination of s and d orbitals that typically make up a band. And so, you could assign that peak structure to that to those orbital levels using that kind of intuition and the density of states diagrams that we've looked at before. Okay, oops. Yeah. So this is a little bit confusing. It took me a little while to wrap my head around this, but this analysis where the onset is defined as the Fermi energy, and then this cutoff where it stops emitting photoelectrons tells you how to measure the work function of the material. It's the difference of that photon energy and the width of this spectrum from 0 to that cutoff point. Is that clear? Anybody want to ask about that? Or want me to repeat it? Silence, we're good. So it turns out, depending upon the material, you can get different work functions here. Okay, so work function again is the difference between the vacuum level here and the Fermi energy. And that's the minimum energy required to remove an electron from the solid. So various metals like cesium, calcium, aluminum, and so on have different work functions. So it's perhaps not surprising that something like cesium has a very low work function. Okay, because cesium is very good at giving up its electrons. It's a powerful electron donor. It's a potent reducing agent. So popping an electron out of cesium and into vacuum should be relatively easy. You go down toward osmium and gold. Gold is an electronegative metal. It doesn't oxidize easily. Platinum doesn't oxidize easily. It wants to have a full valence shell. They're on the right-hand side of the transition metal series. And so it takes more energy to get electrons out of those metals, and therefore their work function is higher. You can see on the right here the ionization energy of the gas phase atoms. They track the work function pretty well. Some of these things are a little bit hard to predict, but in general, the ionization energy of the metal and its work function sort of go together. Now you'll notice some of these things have a range of energies. So gold is 5.1 to 5.5. And it turns out that the surface structure of that material will change the amount of energy it takes to remove an electron from it. So if you have a piece of aluminum foil, for example, it's going to have a coating of aluminum oxide. And if you put it into a photoelectron spectrometer and you measure it, you're going to get a different work function than if you have a freshly cut piece of aluminum or one that's cleaned under vacuum using an electron beam. That aluminum is going to have a very different work function because there's not this oxide layer in the way. Okay, so it turns out the work function of a sample is not necessarily an intrinsic property of the underlying bulk material. It's also modulated by the surface. Yeah.
Sorry.
Go
So
ahead.
on the previous slide, it was the 111 face of gold. So if you did a different face, would that also change?
Yes. Yeah. So there are electric fields that develop. I need to make some slides on this topic, but there are electric fields that develop depending upon which atoms are present, whether that surface is polar, how coordinated it is, etc. Okay. Crystal symmetry is another one of the things that impacts that. So you can end up with a pretty wide range of work functions. And people use this to change their devices around. Okay, I mean, if you're trying to make an electrical device where you're injecting charge from a metal into a semiconductor, you want to have the work function of the metal that you're using align with the sample that's receiving the electron, right? You dump this electron in, or maybe you're pulling an electron out. You want that energy to sort of match in a way so that the electrons flow in smoothly and they don't lose a bunch of energy. And so people pick different metals, but they also modify the surfaces of them to change the voltage of the electron that's coming out or going in. All right, so in addition to photoelectron spectroscopy, there's also X-ray fluorescence. So you can take a core level, promote an electron, And that electron, instead of becoming a photoelectron, can become absorbed. Okay, so this is different than photoelectron spectroscopy. This is now X-ray absorption spectroscopy. And this transition is like any other transition in the material, right? There's a HOMO-LUMO transition or a D to D transition or an MLCT transition. This is an X-ray absorption transition, and it involves an electron from a core level being promoted to some other level within the material. In addition, you can have fluorescence, where a hole that's generated by removing an electron, for example, in a photoelectron spectroscopy experiment, there'll be a recombination event where an electron within this material drops down to that hole, and the energy spacing gives off a photon corresponding to that difference between the electron that is recombining with this hole. And so you can use the X-ray emission that comes out of that as another way to analyze a sample. So as we said, the core orbital energy levels are really well defined in solids and in molecules because they don't make bonds. Okay. They do get modulated slightly by changes in the electronegativity of the atom or its effective nuclear charge, right? If it's an electron deficient complex, for example, the nuclear charge is going to be slightly more positive, and that can shift the core orbital energy around, but its width is always very narrow, okay? And that's great for these types of experiments because you can just assume a single level, energy level here for the core orbital, and then there'll be some breadth associated with whatever level it goes into. But the starting point is very narrow in energy. So that's very useful. The other thing that comes into play in these types of processes, absorption and fluorescence, is the probability of those transitions. And that probability is a function of the orbital angular momentum selection rule. Okay, so it's got to have delta L of plus or minus 1 for it to be allowed. So if this core orbital is an s orbital, then it will accept an electron from a p orbital level, but it won't accept an electron from an s or a d because the delta L for that transition is not plus or minus 1. Same is true for the absorption process. Okay, and so that gives the spectrum more information, because the probability tells you about the type of transition. And in this case, it tells you about the orbital angular momentum of the source of the electron or the place that the electron is being received. So that gives you a method to analyze the orbital structure of the material. Right, so in one case, the absorption case, it's the strength of the absorbance, and in the fluorescence case, it's the strength of the emitted light. So let's take a look at an example here of the X-ray absorption and, X-ray absorption and fluorescence spectrum of silicon. And this is the emission spectrum from a K orbital. And this is the emission spectrum from an L orbital. And you'll notice that the photon energies that are being measured here are very different. So on the bottom, we have 90 to 100 EVs. On the top, we have 1800 EVs. Okay, and that's a product of the depth of the electron. So the K orbital spectrum is the first energy level. The L is the second energy level. And in this case, it's a 2p orbital. So the hole that the electron is recombining with resides in this set of 2p levels. In this case, it resides in this 1s. So when the electron falls down, you get a much higher energy X-ray emitted. And in this case, you get a lower energy X-ray emitted. And that explains these photon energies down here. Now, this transition, as we said, has orbital angular momentum selection rules applying to it. So now we're transitioning to an s orbital. And that means that the electrons that drop down are going to come from p orbitals primarily. Whereas in this case, we're transitioning to a p orbital. And that means that the electrons that fall down are going to come from s orbitals. So the spectrum that one obtains is this broad spectrum spanning 10 electron volts from 1830 to 1840. It has approximately 2 features. Down here, we have another spectrum that, again, is about 10 electron volts wide. And it has 2 features. And the ratio of these features here is very different than the ratio of the features down here. Okay. So let's see here. Right. So as I said, the width of these bands that you're looking at is about 10 eV wide. That gives you an estimate of the valence band width in this material. Okay. For both of these measurements, we're looking at, we're going to L equals, or going from to S and to P's, and that means you can probe all these different levels. And that makes this spectrum, these 2 spectra, a good reflection of the width. So the width of this band here in silicon is about 10 EVs wide, and that's why this fluorescent spectrum is about 10 EV wide. Notice how the ratio of those 2 peaks is not the same. So the low energy photons on the low energy side, those things are going to come from the bottom of the valence band. They're closer to the 1s orbital. And so those low energy photons here come from orbital states down here. The high energy photons come from the top of the valence band. And notice in this case, those photons that come from the top of the valence band here are very intense in this K orbital spectrum, whereas these ones are not. Down here on the bottom, the opposite is the case. This band here is very intense compared to what it looks like up there. And that tells you that the low energy part, or the bottom of the valence band, has a much higher probability of transitioning to that 2p acceptor level than this, the low energy region of this band. And so it tells you that the top of the band here has a high probability of transitioning, and that must mean that it's composed primarily of silicon P, or 3p orbital functions. Whereas in this case, where you're transitioning to a 2p band, you get high intensity down here at the bottom of the band, and that suggests that the bottom of the valence band is more enriched in s orbital character. And this makes sense if you think about the splitting of the 3s and the 3p levels of the atom. S is below p because it penetrates the nucleus more effectively. So looking at the relative peak shapes and intensities of these 2 transitions allows you to analyze the angular momentum of the orbitals at the bottom and the top of the valence band. All right, Margot.
Does this mean that the valence band is also like in some ways quantized if there's like a high and a low part of the band? Like I've always thought of bands as like somewhat continuous, and so that there would be like not 2 distinct transitions, but a more like broad feature as a result of it being a band. But we can attribute different sorts of character to different parts and expect it to be like bifurcated in this case.
Yeah, and another way to think about this is the density of states in that band is not sort of a round blob like some of our earlier drawings, but actually is itself featured. I think in the bulk material, it's fair to talk about the band as being continuous. But its density of states is interesting.
Okay.
It's more dense in certain regions than others, and that's a consequence of how the bonding is made in that band. And we're going to take a look at that here in a few slides. We'll start talking about that.
Okay, so like the rectangle that we have here is kind of like a crude picture of the valence band, whereas the density of states would give us a better sense of these things.
Yeah, this doesn't show you the density of states at all. It just shows you the energy levels.
Okay, thank you.
Energy spectrum. Yeah. Anyone else? Okay. So these kinds of games, transition metal chemists love them, and they look at transition metal complexes and speculate about, which orbital is which, compared to calculations of orbital energy levels, for example, and try and derive a sense of, what is the HOMO or the LUMO in my compound, and what does that say about how it might be reactive? All right. Okay, so photoelectron spectroscopy measures kinetic energies of electrons, and then you derive things like the work function and the binding energy from that. You have to remember that the Fermi energy is sort of the highest electron energy in the material, and the separation between that and the vacuum level is what's called the work function. And so you can figure out, what that work function is by using this principle that there's like this cutoff process and an onset and the photon energy to sort of break that thing apart. Ultraviolet photons are used to look at valence bands and molecular orbitals in solids and molecules. And it's a pretty powerful way to analyze materials, depending upon the material. That UPS spectrum tells you a lot. It's an interesting way to look at semiconductors and materials that have impurities in them and all kinds of fun stuff. All right, scattering is a big deal. Photoelectron scattering creates background signal that has to be considered, and it sort of reduces the utility of photoelectron spectroscopy by blurring spectra and making it difficult to integrate them and that kind of thing. But scattering also makes photoelectron spectroscopy surface sensitive, and that's quite useful. And then, as we talked about, X-ray fluorescence, this recombination process, but also the absorption process, obeys the orbital angular momentum selection rule. And that's great for doing orbital assignments. Okay. All right. So we're going to spend some time talking about band structure in more detail now, using Roald-Hoffmann's approach, which is just a simple linear combination of atomic orbitals approach, like the one we used in inorganic chemistry this last fall. All right, and so you're used to this picture where if you take two hydrogen atoms and you put them together, you get a bonding and an anti-bonding combination. And the energy spacing that you get here depends upon the strength of that overlap. And we're going to denote this by beta. Okay, beta is just a generic measurement of the orbital interaction energy. Now, if you take three hydrogen atoms and you put them together in a line like this, and you do this same experiment, they overlap with each other, and you end up with three MOs. But this time, you've got one down here that's the all bonding combination, no nodes at all. And as you go up to the second and the third, you add a node. And you add a node in a way that symmetrically splits up the thing. So the first node goes through that central hydrogen atom. And then the next level where you've got two nodes, those two nodes fit between those two p orbitals. And it gives you a molecular orbital that changes sign as you go from one hydrogen to the next. That's a three-level system, again, with this interaction potential or orbital interaction energy called beta here. So this game continues forever. So you can keep adding hydrogens in a chain and keep making molecular orbitals like that. Here is an example of that kind of thing using p orbitals instead of s orbitals. So now we've got a chain of parallel p orbitals. So you start off with this one here on the left. You put two together and you get a bonding and anti-bonding combination. You put three together and you get all bonding down here, all anti-bonding up here. And in this case, it's sort of non-bonding because you got this node running through that one carbon atom. So there's not a strong interaction between the p orbital on the left and the right. You add one more p orbital and now you've got 0, 1, 2, and 3 nodes. So there's some good bonding going on here. There's some pretty good bonding going on there. Here you've got 2 nodes and 1 bond, and here's 3 nodes, no bonds. All right, so over and over and over, you can increase the number, you add nodes, and you just make sure the nodes are symmetrically put into the structure, and you get very reasonable molecular orbital representations like that. So you can think about this collection of orbitals as defining a band. Now, it's not a band if you only have 6 or 7 or whatever, but you can imagine in a crystal where you have many orbitals, you know, a sheet of graphene or something like that, you end up with this game and a very, very continuous collection of various levels on top of each other. So at the bottom of that band, you have the all bonding combination. And at the top of that band, you have the anti-bonding one. So you can also see the same sort of thing in benzene. And, you know, we talked about in class last fall, this thing called the frost circle. The frost circle takes the shape of the, I'm sorry, I'm yawning like crazy today. The shape of the ring that you're putting together, you put it inside of a circle, point down, and then at each bend in the ring, you get an orbital. So here they are. There's a line drawn for each carbon atom here. 1, and then there's 2 for this guy, and 2 for this guy, and 1 for that guy. And the energy of those various MOs is just alpha, which is the starting energy level for a p orbital, minus twice the interaction energy, and minus once, you know, and then +1 and then +2. Okay, so there's an energy that you can calculate using molecular orbital theory here. Here's the expression. As you go up, you'll get these various numbers depending upon what the angle is that leads to that carbon. And then, of course, here's the molecular orbital diagram version. There's alpha, the various MOs, and there's their structure. Again, the one in the bottom is totally symmetric, no nodes in between p orbitals. And as you go up in energy, you add a node. The first one, single node, symmetrically arranged, and 90 degrees. Those 2 different directions are indistinguishable in benzene, so it's doubly degenerate. You go to the second pairing of 2 nodes and you do the same thing, this time 45-degree rotation. And then finally 3 nodes all the way there at the top. Okay, so the same ideas work in crystals, and that's kind of Hoffman's approach. Here's an infinitely large ring of p orbitals. And in an infinitely large ring, down here at the bottom, you have the totally symmetric combination. And up here at the top, you have this alternating plus minus plus minus plus minus arrangement. And then there are many different other MOs in between that have varying degrees of bonding character down here at the bottom and anti-bonding character up here toward the top. Okay, so crystals are very much, and semiconductors and metals, you know, they obey the same kinds of principles that you see in the orbital diagrams of simple ring systems like the one shown here. All right, so there's this thing called a block function that can be used to derive molecular orbital functions, and we're going to go through learning how to use that. And, you know, there's this, let me see what time it is here, because I don't want to jump into a topic that we're not going to be able to finish. All right, so this guy, Felix Bloch, developed a method for generating molecular orbital functions using what he calls a block function. Here's the block function for a given wave function psi with this index here, k. This k value is kind of like the 0, 1, 2, 3, 4 in the previous slide. And because of the fact that, you know, as you go from 0 to 1 to 2 to 3 to 4, the MO changes. Hoffman talks about this k value as being like an index that describes the symmetry of the molecular orbital. Now, there's a linear sum here of this e to the ik function which is basically the block function. And it's helpful to remember that e to the I k x, this generic function, is equal to the cosine plus I sine description shown here on the right. Okay, those two things are equivalent. Okay, so this function is really like a cosine and sine function. And that tells you it's going to be kind of a periodic thing. All right, so we're going to use this function and a linear chain of hydrogen atoms to build up molecular orbitals to illustrate why this is so good. Okay, so we want to be able to generate any linear combination of these guys from 0 up to the number of atoms that are present in the system. There is a separation here, A. Okay, this is the separation between hydrogen atoms in this chain. That's like the lattice constant of the material. And then each atom is given a number, 0, 1, 2, 3, 4. And then we're going to put in component hydrogen 1s functions here into our wave function. Each of these atomic orbital functions are given the symbol chi. So we've got chi, which in our case is a hydrogen 1s function, on atom 0. We've got chi on atom 1. And so each one of those chi's gets a different subscript from 0 out to n. All right, so this function, A over here, chi n, the index of the atom, A is that lattice constant, and then this parameter k, which is the index for the orbital, which orbital we're considering. We can use this function to generate that series. So let's go through that process for a second. So let's take a look, for example, at k equals 0. All right, so that's the lowest energy wave function. At k equals 0, when you take that, where is it? I tossed it out here. So if we put 0 up here above the exponent of in the exponent, now this thing turns into the sum of e to the 0 for each different value of n times this hydrogen 1s function. And so what that says is that this is just a linear combination of chi 0, chi 1, chi 2, chi 3, chi 4. That's the sum. All right. And so when all these chi's have the same sign, we're going to diagram them like I've done here on the left, where they're all shaded in. So let's do the same experiment, but this time we're going to do it for k equals pi over a. So if I put k equals pi over a into our block function now, we get this function e to the I pi n. And you have to remember that e to the I, show that here. E to the I pi is equal, there I put it, is equal to -1. Okay, so if you take this piece and you say, all right, that's -1. Now this is just a sum of these things for different values of n. And the exponent n here converts this from -1 to +1, depending upon whether n is even or odd. Okay, so if we do this for chi 0 with n equals 0 up here, this just turns into a plus chi 0. If n is 1, so this turns into minus chi 1. If n is 2, this turns into plus chi 2. And so what that means is that all of these hydrogen 1s functions here now are adding up into this linear collection of plus and minus versions of the hydrogen 1s function. So this molecular orbital function, this psi 0, not psi 0, psi pi over a, this is a typo, is plus and minus as you go along this chain. Okay, so when you make up molecular orbital functions using block functions, two of the very relevant indices k are k equals 0. That's the all positive combination of the component orbitals. And k equals pi over a. K equals pi over a gives you the alternating plus minus combination of those orbitals. Okay, and you have to, if you look at the block function, you have to remember that e to the I pi is -1. You can remember that. It's pretty easy to see that the pi over a function alternates the sign of the atomic orbital that makes up the MO. All right, so Bloch says, you know, this periodic function makes it really easy to look at all these different combinations, linear combinations of orbitals. And we're going to use this, these values of to generate each one of those. 0 and pi over a kind of happen to be the limits of this. All right, so we're going to revisit this next time. So I'm going to just start explaining this now. In a wave function, you know, or in a molecular orbital system, like an aromatic ring, for example, we went from cyclopropenium all the way out to this infinite chain of p orbitals. Now you have a bunch of different molecular orbitals corresponding to those different values of k, right? So we're looking at different wave functions with values of k. And what we're really interested in doing is going from 0 to pi over a, right? The all positive combination and then the all anti-bonding combination. This is the all bonding combination. This is the all anti-bonding combination. And in these molecular orbital diagrams, here's the all bonding combination. This is k equals 0. And then the all anti-bonding combination, k equals pi over a. So the energies of these levels here are illustrated using this alpha and beta terminology. So in an aromatic system, we've got alpha minus 2 beta here at the bottom. The all anti-bonding combination is alpha plus 2 beta. So because this wave function e to the I k is a linear is a cosine and sine function, you end up with this the shape of this curve that you see here as you go from this all bonding k equals 0 to the all anti-bonding k equals pi over a. So it has this sort of funny looking shape as you go from the bottom of the collection of orbitals to the top. So because this thing is periodic, you can continue looking at other values of k, and it's just going to do the same thing. Okay, oscillating back and forth between e equals alpha plus 2 beta and minus 2 beta. And so generally, when you're looking at block functions like this, nobody ever talks about what's outside of pi over a or 0, because it's just a repeat of some of the ones in the same region here. So this range of values is what's called a Brillouin zone. Okay, and typically we only analyze wave functions that have 0 to pi over a in their indices. So this is just a different way of representing a molecular orbital diagram. All right, the difference is that it's plotted as a function of this thing k, which is going to get more interesting as time goes on. But it's the same thing that you've been looking at before. There's a bunch of different energy levels, and each one of those levels represents an infinitesimally small point on this line. Okay, so many orbital energy levels make up this line here. They have this energy relationship versus k that oscillates in this manner. All right, so we're going to go forward using that to build up more complex diagrams, you know, like the molecular orbital diagram of graphene, for example. And we're going to get good at using these block functions. See if you can go back and generate some of these functions on your own, or when you're reading through the Hoffman text, make sure you understand this. It's not too hard. You know, you just got to plug and chug a little bit to get familiar with that. And with that, I think I will stop for today.